yesterday, they asked me for copies of these notes, so after this lecture I will put on that table the remaining copies I have, and you can just pick them. Secondly, please ask questions during the lecture. This morning I had a session answering questions. I will come every day 15 minutes early to explain questions you have. We didn't have enough time, so tomorrow again there's more questions than time. I'll make it earlier. So tomorrow I'll be 8:45 to answer questions you have. Now, the reactions were mixed on my talk yesterday, I'm told. On the one hand, people liked my anecdotes. Secondly, the people who worked it all out are told lyrical, which is nice, but they are not everybody. And some people say, what the heck is he doing? So let me again say what I'm doing. I'm trying to give you a mathematical introduction to a new field, which was discovered in 76, Supergravity. It was based on an early field called Supersymmetry. It led to another field called Superstring. So I'll concentrate around all these fields, give the mathematical formulation. And for those of you who were not here yesterday, let me recall, this is the simplest model in my 30 year almost of working in this field that I could construct. It's not a model which represents nature. It is a model where mathematicians can see the tricks we do. And those of you who work out the notes should, in principle, have no problem reading the literature. The applications which mathematicians like Graviton and Zyberg, and Zyberg is not a mathematician, and Borbacha and so use, is more complicated than this. They use fields with spin. I will say a few words and a few anecdotes about spin in a moment. But first I want to recall what we did and then go on. So I take a very simple model, and yesterday I discussed that the model was supersymmetric. I gave you the transformation rules of the two fields, a field phi of t, which was an ordered field. I took this field in C infinity, although we also in physics need fields which are not in C infinity. The path integral, there are many more fields than this, but these fields are dense in the L2 sense, so this captures all the things I need. And I put in boundary conditions that phi of t goes 0 as t goes to plus or minus infinity. When you have systems with boundaries, the boundary conditions will be different. That's an extra complication I'm not going to discuss here. String theory, very interesting, is that you have manifolds which are not just Rn, or in this case R1, but which are very complicated Calabi-Yau manifolds, and then you have to do further things. None of these things I will discuss because I want to give you the bare essentials of supersymmetry and supergravity. There are other fields which are denoted by lambda of t, and in the second lecture somebody asked if the speaker was talking about Grossman variables, and a loud laughter ensued. So I take it that that meant that not everybody really understood what Grossman variables are. So let me try once again. One way of finding a representation of these Grossman variables is that for every value of the coordinate t, so t1 for example, you can write it as a constant, in this case a real number, times a symbol. Let me look at the constant a, the symbol is the alpha. If you then look at another time, then I have another constant and another symbol. And this way you can form an exterior algebra, the alpha d beta. So now you understand through this representation that this thing is minus this thing.
You know, it just occurred to me so the physicists use the idea of variables that for each point at the same time, the value of the field is a variable.
Yeah.
Or each point, so
right.
So if you have uncountably many variables,
right,
which take values,
yes,
and like the Grossman.
Right.
I mean, you think of it as a function, but you can think of each point.
You say that each of these things have a one-to-one map with the points of space-time.
Right.
You could do that, but you also need derivatives in these fields.
Right.
So you would need these things and other things. More, say twice or three times. In fact, since you can take arbitrary many derivatives, I need arbitrary many of these, as many as there are points of space-time. So it's an enormous case. I prefer not at this point to engage in a careful definition of what I'm doing.
Right.
Let me give a mathematical statement which all of you will appreciate. This is a pool of objects, a lot. That is not a very careful definition, but good for my. And these things have the following rule that the alpha d beta is minus d beta the alpha. From this it follows that the alpha times the alpha is 0. So these rules follow now from these properties. linear algebra. You can add these things, you can multiply them by real numbers, you can take wedge products. It's now what I said yesterday, that mathematicians, and I warn you because this is really a fundamental difference between some mathematicians who use these things and physicists. I need really infinite numbers. Suppose I had a finite base, that is to say I had only the alpha 1 up to the alpha n. If you then take out the products, wedge products, exterior products, then you cannot have more than n factors. Because if you, for example, call an element, well, it is here.
I have a question. If you have another constant variable,
But he didn't finish the comment. You can only take subfinite factors
and then the product is 0 after a certain level. So if I have fields, for example, lambda t1 times lambda t2 up to lambda tn, this would still be non-zero. But if I would multiply it by one more field, it would have to be 0.
Why is that bad?
Now, this is what I'm going to come to. I mentioned yesterday, there's a physical property, I'm not going to explain it, it's called unitarity. The physical meaning is the following, that if you have two particles banging together, then anything can happen. But the total probability should be 1. It cannot be larger than 1, or it cannot be negative. Now, how can it be negative or larger than 1? Because, well, that's exactly the problem of unitarity. In the calculational rules in field theory, sometimes, if you say, I define my probability in this way, and you then compute what happens if two particles bang together, sometimes you get a probability, according to that definition, which is larger than 1. That makes no sense. In that case, we say unitarity is violated. That property, if it violates after a certain number of multiplications, violates unitarity. Now, mathematicians who couldn't care less about unitarity can very well work with this. It's a mathematically consistent scheme. It's much easier to work with a finite dimensional algebra than infinite dimensional algebra. But physicists who like to, in the end, still represent real nature, want unitarity, and so they work with an infinite dimensional Graviton algebra. Now, this is a very fundamental difference, and I stress that part because of all the
But to illustrate the calculations you did yesterday, you could work with these truncations.
Yeah.
And you would illustrate the alpha.
Since yesterday, I only had products of 2 lambda fields. I could have had a basis of 2, and I would not have run into trouble. But then I looked at variation. No, they also were. But in supergravity, for example, which I'm going to comment on my final calculation 76, involved 5 Graviton variables, 5 everybody fields. So I would have needed a basis of 5 at the time. And you can just easily think that more. So to be logical, I have an infinite dimensional algebra. Then I will never run into trouble. It's unitarity. If you don't care about physics and unitarity, be my guest and take any finite basis you like. It's not wrong. Mathematics. Is there any other question?
yeah, if you have a second random variable, say random prime,
Yeah, lambda dot. Always second. Let's call it mu of t.
mu. Yeah. If you have mu of t1,
It's still completely independent of this. So if I now look at mu at different times, t1 or mu at t2, then I write again such a mu as t1 as some real number, p, times some symbol, d zeta.
That symbol is not the same.
This is not the same as the alpha and the beta, whatever.
The alpha are from the same time.
Even if it's the same time, it's different because lambda and mu are different. Now, if I write lambda dot of t, then I write this as yet another real number, times yet another symbol, the eta. And this, again, is completely uncorrelated to the one of lambda itself. So even when I have the derivative at t1, which is somewhere on the board, where you can guess, all these things are independent. So, in that sense, as I said yesterday, formally the DDT is a map from one Graviton variable, lambda t1, into another Graviton variable. But they are completely unrelated. It's not the product of 0 or 1 or anything. Now, before you get the flavor, as general as possible is my Graviton algebra. Now, there is something very interesting, and that is that you sometimes can think, now do a bit of mathematics, coset manifolds. You can use coset manifolds in the mathematical sense, which are parameterized with a finite number of Brook parameters. And then people like to consider a combined exterior algebra with the axis of the base manifold, so dt, or the head, my integral, and dx1, or dx, dy, y, dz for the coordinates. In addition, I can have the alpha, the beta, and that stuff. Then I combine it into the whole algebra. And if I then can identify these d alphas with these of the group parameters themselves are real numbers again, like the group SU2 is exponent I, omega dot 2 with 2 matrix defined fundamental rotation. Then the group parameters are 3 real numbers. So they had 3 d alphas. And people have loved this idea of a cosine manifold, where you have a base manifold and a fiber and making a big space and having this algebra. It fails because you have a finite number of Graviton variables in that case. The group is say SUN and you have n squared minus 1 independent basis elements for your Graviton algebra. And so if you go to n squared, and you actually get 0. And so although I love this idea, there should be something you can rescue of it. Until now I've never been able to make sense out of it, but it is a beautiful idea. Combine, put this Graviton notion in context with group theory and so on. Any other question? Good. Now, so what we then did yesterday, and I will go on now, was that I'm now going to look at charges. And then I do local supersymmetry. I decide maybe to change the order at this moment. I will first do this because it's a high point in my life and hopefully in your life. So I only summarize what I did yesterday. The action will be a bosonic part or a commuting part, and this is phi dot times phi dot, and I discussed that. And this is the product of 2 Graviton variables. In fact, I don't need it for reality. I discussed all that. Then I introduced yesterday the notion of dimension. Phi I computed with you has dimension minus a half. If t has dimension minus 1, and dt therefore also dimension minus 1, and lambda has dimension 0. And then by consistency, I found from this rule, this is the only thing you would possibly write down, and then epsilon by consistency has dimension minus a half, but then the other rule we needed the ddt to make it dimensionally correct. And at this moment, translation is entered. If you have a field, a function phi of t, and you shift it a bit, it becomes phi of t plus delta t, then to first order in a Taylor expansion, you get the old function plus delta t times the derivative of that function. So physicists call it the dt of a function, the translation of a function, because it was obtained from phi of t by replacing t by t plus delta t. T plus delta t is a translation in the time direction. Now, there is a very deep theory behind it, Hamiltonian formalism. Translations in the time direction, the generator is called in Hamiltonian, but we are going to deduce it all. I'm not asking you to believe it. So, in a moment, we are going to interpret this innocuous dot on top of the phi. It's not a blemish on the transparency, it's a time derivative. And it will have the meaning of a translation in time, and this is the crux of general relativity, in fact, as we will see. So you put one dot in the theory of general relativity. Now, how does this go? I showed you the proof yesterday, but when I did the proof with you, I took it with constant epsilon, and I'm now going to consider local epsilon. So at this moment, I do something which now let me give a historical discussion and then I come to it. In the 19th century, people invented theory of electromagnetic field. And then there was a physicist called Maxwell who wrote Maxwell equations down. It turned out electromagnetic fields themselves were derivatives of something more fundamental. There's something more fundamental that had the austere name of vector potential. There's a 4-vector AU. And with the hindsight, people realized that if you wrote these electromagnetic fields as derivatives of the vector potential, then the expression for the electromagnetic field didn't change. If instead of the vector potential, you wrote the vector potential AU plus the d mu of anything, blue cheese or whatever. Now, in the 19th century, people said, well, that is as it is. It probably means that that derivative of anything has no meaning because you can only measure electric and magnetic fields. Then in this century, people did very clever experiments. They took a cylinder, and they shot electrons around it, and when the electrons went two sides of the cylinder, you had a non-simply connected space in which you move it if you look at this plane. And suddenly the vector potential was crucial. You could measure it. Depending on, you had then a cylinder which was completely conducting. Electric and magnetic fields couldn't leak out, and you were very careful by making sure it didn't leak out. But still, depending on what magnetic field was inside the cylinder, the electrons gave a pattern on a photographic plate behind it which was different. So these ANUs themselves are measurable after all. Now, I'm going back now to the end of the 19th century. Around 1920s, I would rather say 20, 22, 24, people started studying another theory called general relativity. It was proposed by Einstein based on beautiful mathematics of Italian differential geometry. It wasn't clear that it was a gauge theory, but after having written it down, people said a similar kind of thing like that happened. You had a field which now is called gravitational tensor, and it was itself expressed in more fundamental fields, metric fields, G mu. And again, if you add it to G mu plus d mu, some vector, anything psi mu plus d mu psi mu, then to first order the observables didn't change. So we had another example of gauge symmetry. And then the mathematician Weil, in 1928, as I mentioned yesterday already, said this property is more important than the equations of Maxwell and Einstein. The symmetry is more important, and that has become now the modern tenet in almost modern theoretical physics. Symmetry is more important than dynamics. Some of us, and I'm one of them, go as far as believing that all dynamics will derive ultimately from symmetry. Certainly Young was one of the early pioneers of this thought, wrote his famous Young-Mills paper. The first part is symmetry and the second part is dynamics. And he was the first, all papers before had dynamics first, and then said, hey, the dynamics has a symmetry. But he said, the symmetry is the dynamics which has the symmetry. So symmetry is very important, and my lecture is all about symmetry. Now, gauge symmetries, turned out that these things and these things, they are...
So you call this fact as a symmetry?
Yeah,
like you can add this.
Yeah, because this anything can be a function of x because it's more general. And then this is called the gauge symmetry. If the parameter I had is constant, so our lecture yesterday actually was constant, then I have a rigid symmetry. So at this point I distinguish between two kinds of symmetries. For us it means epsilon is constant. And local symmetry, sometimes called gauge symmetry, epsilon becomes a function of t, or in the case of these people, space-time. So sometimes the infinitesimal change is written like the change in a nu of x is equal to the derivative of anything, lambda of x. Now lambda is a bad name, otherwise you think it's a Grossman variable. This is not a Grossman variable. So lambda of yeah, the trouble is, let me write it like this. People usually write the word lambda, so I write a capital lambda. Now this is a gauge symmetry, and notice the field transforms from derivative to symmetry here also. Delta G mu, the change in G mu is this thing, and this is a function of x. So again, notice the derivative of the thing. So we have these two kinds of symmetries. Now yesterday I had a lecture on rigid symmetry. But now I want to study what happens when you make the parameter local. And I'm now following a paper by another mathematician, Nieuwenhuizen. And you really take the paper, I'm going to step by step use that paper to construct supergravity. And how do we do that? First, because I want a series of parameter which is now dependent on the coordinate t, I will go back to my calculation yesterday, and already that's epsilon no longer be constant but a function of t. So I roll again through the proof, but now each time I get a dt on epsilon, I don't throw it away, but I keep it. So I get an epsilon dot. But an epsilon dot is just a Grossman variable, as I explained here, like any other Grossman variable. So here's now the proof which I did yesterday, but now mended by having extra terms with epsilon dot. So we had in term 1/2 phi dot squared. The first one, if you vary it, you have two phi dots, but they are the same, so I can just as well vary 1 and multiply by 2, and the half goes away, so then I get phi dot times the variation of this thing. Now I will take this epsilon no longer to be constant, but a function of t. So when I work it out in the second line, then I will get two terms. The time derivative can hit epsilon or lambda. If it hits epsilon, you get this term. If it hits lambda, you get this term. So these two terms come from this term. We're using the distributive property of the time derivative, the ddt. Then the next term was the variation of lambda in here, and I will do separately the variation of lambda. Well, the variation of lambda, and I put lambda in front, writes it easier, then you have the minus sign, and then here, no, I didn't put lambda in front, but lambda varied into minus phi dot epsilon, we saw yesterday, so I write that here. And then lambda dot is the ddt of lambda, and here again I put the variation of lambda, which was minus phi dot epsilon. So this is the variation of lambda, which you get here, and this thing. Now yesterday I partially integrated this term. I didn't like a phi with 2 derivatives because nowhere else was a phi with 2 derivatives. So if I partially integrate, I get a surface term, boundary term, and then a derivative on lambda. So I'm using here the standard integration by parts because t is an ordinary integral, it's an ordinary variable. It's nothing cross from t is. So and we all know how to partially integrate as calculus. So I'm using that. That is really very elementary. And then I noticed yesterday, and it still is true, that these three terms cancel. You have to be very careful about signs and factors of half. The 2 halves, they end to 1, and there's another 1 here. The signs are fortunate so that they cancel. So then I'm now left with 2 terms. Yesterday I had 1 term, the boundary term, but now it's 2 terms. There's a term is epsilon dot, and there's a term is ddt. Now I argued yesterday the boundary condition is such that the plus and minus infinite time, phi and phi dot and all its derivatives go to 0 sufficiently fast that anything vanishes. Now here I have a little problem. What do I mean by saying lambda of t goes to 0 at infinity? Lambda of t was a Grossman variable, and I can't say that the Grossman variable is very small because I don't have the norm in Grossman space. So strictly speaking, this is an ill-defined concept. I've never ever in my life seen any physicist making this remark, but since you pressed me yesterday a lot, I decided to say a few words about it. Now, the words are not easy. So, those of you who find it already difficult, now think of holiday, and we come back to the simple thing. But lambda of t, in the quantum theory, becomes an operator. Physicists like to put a hat on a symbol to indicate it's an operator. And what we mean that lambda of t goes to 0 is that matrix element between states A and B, this wave package here, these things tend to 0 as t goes to infinity. Now, this is a difficult thing, and it already assumes the quantum theory, which I haven't reached yet. I'm still completely clever. But in this sense, so this is the weak sense that we call. We have operator sense, which some people call uniformly 0. We have an operator acting on a state. We call that, if that goes to 0, we call that strongly 0. And matrix elements, we call that weakly 0. So in this sense, I say that field lambda t goes to 0 really means in the quantum theory the matrix elements go to 0, so it's weakly 0. Now in that sense, one should reinterpret.
We use the same terms.
I used to say, oh yeah,
Yeah, we use the same, exactly the same terms.
That's why I do it. I want a mathematician.
No, they're the same terms.
That's why I do it. So, then I dropped this term. Now, there was a long talk, and actually, this is a difficult problem. Physicists in the room who know the horrible words LSZ, which is even today not understood, it's that kind of problem here. So I think there's work to be done for physicists to do this better. But I have given you a direction, a thought in which you can justify it. So now I ask you, whenever I write lambda of 2 of t and then let t go to infinity, to still put such terms to 0. Now, then this term goes away and I'm left with this term. So from here I will now pick up the discussion and construct Supergravity. Yeah, first, well, let me start straight away.
So this difficulty would appear in somebody's normalization rule, and we
if you want to remove infinities, you should also remove infinities and infinity. So when you have boundary terms, or you have fields which do not go to zero, now here all my fields go to zero, but when you talk about topological properties like winding numbers, Gaussian fields, they don't go to zero, they have a non-trivial twist, then in the realization to study such boundary terms. But I'm not touching that here, so there's no topology. So the answer, in fact, is yes, they play a role, but they come on top of the usual things, which I'm going to discuss. Now I have to go back to my notes for that reason. So we have seen now that the variation of that action, this, I'm now starting from this result, is equal to the integral. I will sometimes omit writing plus or minus infinity. Epsilon dot I phi dot lambda dt. Now in general relativity in 1920 and in Maxwell theory even earlier, it was realized that you needed engaged fields for local symmetry. Weil had the absolute amazing idea that when I have a local symmetry, you need engaged field, and engaged field leads to forces between the objects. When you have the sun and the planets, there's a force, the gravitational force is due to the gauge field, the gravitational field. So gauge fields, by being exchanged between other objects, lead to a force. So you need an engaged field in this theory. What could possibly be the gauge field?
Well, what do you mean when you say gauge field?
I mean,
In this context.
in this context, I need, in this context, I mean, firstly what I'm going to do then. So I want a gauge field which gets rid of this term. I want an invariant action, but now instead of local I got a variation that didn't cancel. I want to get rid of it. So I'm going to introduce a new field, which I call psi, and I give it the name Gravitino. And the reason it's called like this, it is the fermionic part of the graviton. The graviton is the content of the gravitational field. In the old theory of general relativity of Einstein, the gravitational field was g mu of x. Now light, which is defined by a vector field a mu of x, according to the quantum theory of the 1920s, consists of little bullets on top of each other. Each bullet is called a photon. So this light is not continuous, and little staccato, all these photons are hitting you. Gravitons also, when you have gravitational wave radiation, it has indirectly been found, no algebra has been given for it, but not yet directly found. People all over the world are now having enormous detectors to detect gravitational radiation. Radiation will also be little bullets, in the detector, this like a war machine. Staccato hits with all these little gravitons. Gravitons are quanta of the gravitational field. These particles, which are quanta, little bullets, have fermionic friends, according to supersymmetry, and they're called Gravitinos. These are particles, and in physics, a point particle is equivalent to a field. And a field can be used to describe a particle, a duality between particles and fields. So the Gravitino particles need a field, and in my simple model, this will be psi of t. Since it's the gauge field of an anti-Graviton Grossman, and fermionic as we say, because we call it after Fermi symmetry, this gauge field will be anti-Graviton again, and Grossman variable. And using this field, I can cancel this variation. And this is now the crux of the idea. In Emmy Noether's article, if you look it up, she says when you have a rigid symmetry, she doesn't call it epsilon, but the rest is from her paper, and you make it space-time dependent, then the action will no longer be invariant, but there will be terms proportional to the resonance of the graviton. And the coefficient of these terms she calls current. And so in this case, it's a current. The people have been nice to her, and we call it a Noether current. So this is the supersymmetric Noether current. And now, what in 76, procedure, we can do everything by hand. So I'm reliving 1976, except that it's much easier. I can add now a new term to the action, which I call S neuter. And I can write it as follows. I can write it as minus psi I phi dot lambda dt. So I have two Strasbourg variables here, an ordinary field factor I minus psi, and I stipulate that the variation of the new field psi of t is equal to epsilon dot of t plus possibly more. So I will write dot. We will see that is more, but it will come. And now I claim that if I vary the psi in here according to this rule, I get a term which precisely cancels this term. So I've constructed a new field and its transformation rule, and the only aim was to cancel this variation. So let me say it again. If I vary this psi according to this law, I get the epsilon dot, which is a minus epsilon, I phi dot lambda. Here I have plus epsilon dot I phi dot lambda. Some of these two terms cancel. Now, however, we are not done, because I've added a new term to the action, and I've varied this field. But when you have a term in the action, you should vary all fields. So there are two fields I haven't varied yet in this new action. It is this field and this field. And now what I'm going to do is the neuter procedure.
So we have those fields that make varied by the formulas you gave last time.
Yes, so I'm going to use these formulas in here. You are entirely right. So let me write it down.
Oh, so you add us today?
Yeah.
Okay.
No, that's correct. No, so I'm going to use this formula. However, epsilon is not a function of t, because that's the new game I'm playing. And I'm going to use that in here. Here, in the original action, I varied already everything, so I don't have to do it again. But I got this extra term. That was this term. This term I cancelled by adding this new term to the action. But the variation this term cancelled that term. Now I have to vary these two things. So I get new variation. So the variation of S neuter is, and I will get two terms. One for varying phi dot and one for varying lambda, according to these two rules. Let's see how far we get. And then I try to get rid of these terms. And then I get new variations. And I try to add new terms, both to the transformation rules and to the action. So I'm going to change order how far I go as I go along. And you may think this is an unending procedure. Each time you add a new term, you need new variations, but it always terminates. And I can even prove that. I'll show it explicit in this model. So it's a general proof which takes me some time, and it's not interesting because I want to stick to this model. So I know it will terminate. And when it terminates, I have an action, which is a sum of the original action, plus whatever further terms I have. And it is invariant under these modified transformation rules, namely the transformation rules of the fields phi and lambda I had already, but also the transformation rules of this field psi. That's in 1976 what I thought would be the whole story when I started. And then a disaster struck. I found variation I couldn't get to. And I would like to bring you to that point, because at this point something very beautiful happened. Now, in order to prepare you for the breakthrough in thinking that happened, I go back now very briefly to the rigid model. So we must switch back to where we were before, where the parameters were still constant. And I mentioned yesterday already that I was going to show, here it comes, what the commutative symmetry is. When mathematicians have a symmetry, they like to look at the algebra of symmetry. They don't take probability symmetry, but they take commutative, because that forms a group structure. Now, you're familiar with that, this order symmetries, like group transformations. You can have a transformation group acting on carrier space, and you can see how two transformations act on an element in carrier space. So in this case, I would call phi and lambda the carrier space. And the symbol delta epsilon is the action of the symmetry algebra on the carrier space. So if I now make two such transformations, first one, and in the result I make the second, if I make the first variation of phi, I got I epsilon lambda. But then on the result, I make a second transformation denoted by delta epsilon 2. and only fields transform. So I got substitute here for delta epsilon lambda, that results for lambda, which was minus phi dot epsilon. So then you get here the I epsilon 1, the variation of lambda was minus phi dot epsilon 2, and because I have a commutator here, I just take the same minus 1 and the 2. And now you probably can see, because epsilon 1 and epsilon 2 are Grassmann variables, if you interchange them, it's the same as taking twice this term. Because epsilon 1 and epsilon 2 is minus epsilon 2 epsilon 1. So it can be written in this simple formula. It is an object, an even element of the Grassmann algebra, you might say, two attributing object. It acts, as I said yesterday, as if it was a commuting object, times and phi dot. Now phi dot was the translation generator. I explained that if the field function phi of t is equal to phi of t plus delta t, you do first order Taylor expansion, you get delta t as phi dot. Phi dot is the translation. So apparently the commutator of two supersymmetry transformations is equal to a translation. People like to say that supersymmetry is the square root of translations. Square roots have an enormous history in physics. Early in the century, in my opinion, the greatest discovery in theoretical physics was the invention of the Dirac equation. And the Dirac equation was a square root of the Laplacian in 4 dimensions, which we like to call prime order equation. That was done, and it led to the Dirac equation. And earlier, I told you yesterday, they didn't want to publish his paper on the Laplacian because the levels came out wrong. Well, Dirac calculated the levels as his square root, and they came out right. And even today, we use it completely as he wrote it at the time. This is one of the pinnacle achievements of this century. So the Dirac equation was very successful. Take the square root. Here we see a second square root in physics. There's no indication at all that this square root has any physical meaning. 5 years from now, maybe 7 years, we will know. It can be total disaster all over the world. These people who got faculty positions should be fired, because I hear my retirement, so that's not. Or it will be the revolution as big as quantum mechanics and relativity. So the verdict is out. Please read the New York Times. You see a big later supersonic particle was found, and we're all happy.
100% is suicide.
Well, if it is found, what did you say? Some other professor may commit suicide. So, now the same algebra I'm going to do with your work on lambda. So the message is that supersymmetry transformation, two supersymmetry transformations. Now I come to an idea. Suppose I make supersymmetry local. Then I get two local supersymmetry transformations, and these are now local supersymmetry transformations. You would expect that it leads to a local translation. What is a local translation? A local translation is that if here's an object, you move it over 5 centimeters, and here's an object, you move it over a meter, and maybe here you move it in the opposite side. Different points, you move it in different directions. That's what is a local translation. In mathematics, you call such a thing a general coordinate transformation. The general coordinate transformation is precisely the same kind of if you're more physical. If you're physical. Well, should have said it. So, now the question was, Einstein in 1960 had a friend, Grossman, not Grassmann, although some people write Grassmann, but they mean Grossman. Independent elements. And that friend had taught him about differential geometry and that local general coordinate transformations, Einstein used it in his construction of the theory of general relativity. So I was aware that Einstein had studied local translations, and it led to the theory of gravity, which is a gravitational field. So when I in 76 looked at this problem, it seemed to me that when I discussed local supersymmetry, I should somewhere along the line find the gravitational field, because local translation leads to local supersymmetry leads to local translations, and Einstein showed that local translation is related to gravitational field. So we expect a gravitational field. Now, at this point we don't know. We have only one field, and this in Gravitino we found it here to cancel this term. But we don't know yet that it is the fermionic partner of somebody. But we know already that for every bosonic field there is a fermionic field, and for every fermionic field there should be a bosonic field. There's a symmetry see these two things.
I mean, actually,
Well, you hope, you hope, you mean.
I hope. I don't know at this point. I know, but the lecture we don't know. Right. So there's a track. There should be both on a quadrant track. Now, so now I have to tell you about spin for a moment. And then I will say I don't need spin, but the anecdote is too nice not to tell. And by the way, if I'm going too slow, tell me afterwards next time.
Oh, perfect.
Well, the electrons, which were discovered in 1896, no, 1898 by Thomson in Cambridge, were believed to be little bullets with an electric charge, and that's all one knew at the time about them. But then people looked at spectral lines, that is to say these electrons go around the nucleus and when they fall from one orbit to another they emit light, and that light can be analyzed and it has a certain frequency. That's called spectral lines, or energy level. Now it turned out that different substances, if you take kitchen salt, natrium chloride, it had some yellow lines and so on. You took different substances that had different lines. But sometimes if you look very carefully, the lines were two lines very closely together. At least some people thought so. But there was this Dutchman, Mr. Goudsmit, and he was a student of Ehrenfest. Ehrenfest, to say the sad story, he was a student of Boltzmann. And Boltzmann committed suicide. Ehrenfest committed suicide. And his disciples committed suicide. I know a descendant of that branch, and each time I look at them, I look at because you brought up suicide, a long register of anecdotes. Now, Goudsmit was a student of Ehrenfest. Ehrenfest was somebody very careful lecturing. He liked to be in the left upper corner of the blackboard and enter in the right lower, and then the lecture was finished. And so Goudsmit said to him, I have to go to Germany with my father, who was a cloth merchant, and I have to miss some of your lectures. Ehrenfest said, this is impossible. My lectures, how can you miss them? Because my father's an invalid and I have to help him. By the way, Goudsmit was in Brookhaven after the war, sorry. And no, Ehrenfest said, okay, you can do that, but then you go to Paschen. Paschen was one of these people who looked at spectral lines, and he went to Paschen in the laboratory when his father was doing cloth merchandise. And he said, yeah, look, and he said, you're split. Said Paschen. We know that very well. That's because the apparatus is not perfect. Now, Goudsmit said, can I look somewhere else? You're split again. He said, yeah, I just told you, we know the apparatus is not each time. So he went back to Leiden, and there he was sitting with Untitled. He was later professor.
Could you speak a little bit?
Yes.
Very interesting story.
Yes. That's more interesting if you discount here. That's twice as nice. For me also. No. So, Uhlenbeck heard about this, and Goudsmit said, it's funny, each time I have a formula and I put some effective tool, I can predict where the line is. And then Uhlenbeck said the famous word, Goudsmit, you have discovered a new degree of freedom. And Goudsmit after
Grossman variable.
Physics is multi-dimensional, not linear. So, then Goudsmit later said, well, when Uhlenbeck said that, I didn't know what he meant, but I knew one thing. I would multiply by 2, I could predict where the line was. That was for him good enough. So then we went to Ehrenfest together, and we said, you know, all these double lines, they're not errors in the apparatus, they're really there. If you multiply by 2, you can predict it. Then Ehrenfest said, well, and then he said, maybe the electron's little rotating ball has spin, as we call it, spinning. And then Ehrenfest said, let's calculate. If you take a ball and you rotate it around, what is the spin? And it turned out everything was wrong. It was in violation of special relativity and all kinds of things. So Ehrenfest said, it's complete nonsense. And then he said the historical words, however, you are young enough to allow you a folly. Sie sind jung genug, um sich eine Dummheit leisten zu können. He spoke German, he was Austria. And so these two people then wrote a little article, which I was yesterday looking up. We have Zeitschrift für Physik, you can see it. And that is the discovery of spin. Now how come? It's one of the big discoveries of the century. And by then all spectral lines were explained, making it so. How come they didn't get a Nobel Prize for this? Because there was an other Dutchman, and his name was Kramer. He was a student not of University, but of Pauli. Pauli was the worst person we could have in advisor. So critical. He was also a very good physicist, and actually, the more people say bad about him, the better I like him, because he was also very honest. But he was not so kind. And so Kramer came to him early in the house from Ulenbeck, the same thing. And Pauli looked at it and said, the same as Ulenbeck, it's complete crap. He said, tear it up. And what did Kramer do? He tore it up and threw it in the waste paper basket. And then when the Nobel Committee was studying who should get the Nobel Prize for spin, he was a problem. Everybody knew Kramer had discovered it, but there's no published record, and you can only give a Nobel Prize for published record. And that's the reason why spin never got a Nobel Prize. Now, that was a story about spin. And when I now look at this gauge field, it has spin 3.5 in my real theory. And the gravitational field, G mu, has spin 2. Now I'm not going to explain that, but those of you who know this about thing, it has two indices, mu and nu. And this one has one index. It is a spinner with a vector index. So 1/2 plus 1, the representation of the rotation group, contains 3/2 and another half. And if you take two vectors, they have spin 1. derivation, if you like. Variation is like a derivation in mathematics. So, and the result is these two terms. Now the aim of the game is to get rid of these two terms. And now there was this field psi, but I noticed that the original action, now there's this variation. So let me copy this on the board here. So I got the variation as another. I psi, the integral, I psi, phi dot, plus lambda dot dt. And I must get rid of this term. And this is an epsilon. Excuse me? Epsilon. Oh yeah, there's an epsilon. Epsilon. I. Oh yeah, there's an I, so let's do it right. I think this is correct. Okay, now, how can I get rid of this term? Now, I had read Einstein's work, so I realized there should be a field H in the game. So now I did the following. I add a new term to the action, which I call S press. It has the following form. Minus H, phi dot. We'll do another term next. Let me begin with this term. And now I can say that delta H transforms into I epsilon psi. Minus I epsilon psi. So if I now vary this H according to this law, then I get the plus I epsilon psi, the two minus signs cancel, times phi dot. But here I had plus I psi epsilon phi dot. So in one term we get epsilon psi, and in the other term we got psi epsilon, it's the same sign. But because these things anti-commute, the sum of these two terms is 0. So by this procedure, I've done two things. I have introduced a new field H, and that will be the gravitational field of Einstein. And I've also cancelled the first variation. What about the second variation? The second variation can be cancelled in the same way, because if you vary H and I add for lambda the same. So I can add an extra term minus H and then I lambda dot dt. So I'll call that the second term S stress. S stress second is. And if I now vary H in the way I did, then you get plus I epsilon psi, and here these two terms cancel also. So at this point, I have varied all variations here. But I have now two new terms in the action, and although I already used the variation H,
this is S press 1 and S press 2.
Yeah.
Press 1 and press 2.
so now I have to vary the phi dots and the lambda dots in here. And again, I have to add terms to the transformation over to the action. And doing this, the process stops. Now, I intend not to do it. If tomorrow you come on course early, I'll do the algebra explicit on the board. But I gave you the answer here. But I have been very careful, step by step, explaining that this is a procedure which is well defined and leads to an answer. What more do you want? So the action is the following. First, I have the half phi dot plus I into lambda dot. This is the matter action, I will call it. And this is the action we started yesterday from. There's a bosonic part and a fermionic part. This, by the way, is the Dirac action in one dimension. So that amazing square root you see here, because this thing has two time derivatives, this has one time derivative. It is therefore a square root of the two time derivative operator. The square root of ddt squared is ddt. Now, it's more difficult than Dirac. I mean, if he would have made this statement, he wouldn't be so famous. But when you take the square root of ddx squared plus dy squared plus ddz squared minus ddt squared, Try it, and if you don't know it, I'll give you the answer tomorrow. But that's where Brook exists, but it's not so easy how to do that. He did that. So this is the Higgs boson, this is a fermion, Grossman variable, and here is the Noether coupling. I discussed it next. And the Noether contributed phi dot lambda. This is the Noether coupling. Coupled to a new field, we call it the gauge field. And now the gauge field, because it transforms into the derivative parameter plus 1. Every gauge field always transforms into the derivative parameter plus 1. The Maxwell field, I wrote cos delta A mu is d mu lambda, and then it stops. But if you have Yang-Mills theory, which is an index here, you get something more. But it's always a derivative on the parameter first. So the field psi, which transforms into a derivative of epsilon plus 4, is the gauge field of supersymmetry. Now the field H under supersymmetry transforms in this way. There's no derivative on epsilon here, so we don't call H the gauge field of supersymmetry. Next lecture tomorrow, I will show you that H transforms into the derivative of the translation parameter. So it's the gauge field of translations, and that was that idea which Einstein had already. Local translation leads to gravity, H the gravitational field. And finally, there's one more term I've added here, H phi dot square. That is this term. You may wonder, what happens with this term? There is an ambiguity at this point. I could have done it in another way. This was one way, and this is one answer. But I could have also cancelled this term in a way which I will discuss tomorrow, by adding a new term to delta lambda. This term. And that's what I did, and that's why in the delta lambda law here, we don't only have phi dot epsilon, which I had before, but there's two more terms. So at this point, you see that I have an ambiguity in this great Noether method. I can do, at this point, two things and still get two answers. The answers are related, what we call by field redefinition. If we write a field in the one version equal to a field in the other version times some other field, then you can go from the one formulation to the other and back. Physically, they're the same. Now, I have 2 more minutes and then I'll stop. There's an anecdote I wanted to end with, and it's a wonderful anecdote, and it's nice at the end of the second lecture. When in '76 I was doing this, we have done it pretty fast, but it took months and months, every day, every weekend, 14 hours per day working. Now and then we couldn't cancel things, then we reached this point. And it seemed it didn't work until we realized we could have a Graviton and so on. So each time stopped and it worked again. And it was a very nerve-wracking thing. And then we reached terms with 5 Grossman variables. And it got so complicated with indices that I used a computer program which had been evaluated by my advisor, who by the way got 2 years ago the Nobel Prize for renormalization of Yang-Mills theory. But he made a computer program for symbolic manipulation program, so not numerical, but with formulas. And I used that for these 5 Fermi terms. And with Jan Friedman, who was here in the time, so Ferrara and CERN, we were working very hard. And each time the computer program had a bug and whatever. But finally it was all straightened out. And we knew this is it. And we didn't know it would work. So we had to put it on the computer, and we got 2,000 combinations with 5 spinners. And each coefficient in front was a number, say 1 or 7 or 3. It had to be 0, only then with all variations in the cancel. And I was sitting late at night in a little computer room here, alone, and then Friedman was in Chicago and told me I should phone what happened to the outcome. 3 o'clock at night it was. I was sitting in the room with somebody, a very nice person, who had some personal problems. He was drinking a lot of whiskey, so he was sitting and asking, is it going all right? I am, Jimmy. We were looking at the outcome of the computer program, and before it had always worked, because the first 1,000 terms or so I had already made 0. It was the last 1,000 terms that mattered. And I was looking, 0, 0, 0, 1,200, 1,300, 0, 0, 1,500, 1,600, 700, 800, 2,000, all 0. Now, supergravity existed at that moment. And you may think that I was very happy, because extremely tired.